Welcome everyone to The Explainer. So I am absolutely thrilled to have you here today because we're going to unlock one of the most fascinating secrets in all of electronics. You know, we use our phones, our laptops, and our smart devices every single day, right? And we totally take for granted that they just somehow remember our photos, our passwords, and our data. But how does a literal collection of mindless wires and silicon actually hold on to a memory? Well, today we're going to find out exactly how a single microscopic circuit is multiplied billions of times over to hold your entire digital life. Let's dive in.
Here's our roadmap for today's explainer. 1. The power of memory. 2. Combinational versus sequential logic. 3. Meet the latch. 4. The SR Latch explained. And 5. Taking control with gates.
All right, kicking things off with Section 1, the power of memory.
So, to understand how we build memory, we first really need to understand what a circuit looks like without it. You see, basic digital circuits have a major limitation. They live entirely in the present moment. So, how does a computer actually remember things? A standard logic gate, like an AND gate or an OR gate, reacts to an electrical pulse instantly. The current flows through, the output changes, and literally the moment that current stops, the output is just gone. It disappears. So how does a simple, instantaneous electrical reaction transform into stored data that a machine can recall an hour, a day, or even a year later?
Which brings us to Section 2, combinational versus sequential logic.
To answer that big question, we need to draw a line in the sand between the two fundamental types of logic circuits. First up is combinational logic. Now this acts just like a simple calculator. You type in 2 plus 2, and it instantly outputs 4. There's no memory, no storage, and no sense of the past whatsoever. But in stark contrast, we have sequential logic, and this acts much more like a brain. Notice that green feedback loop? Yeah, the output there is dependent not just on the new input, but also on the stored state from previous inputs. It actually remembers the past to make smarter decisions in the present. It is a total game changer.
Moving right along to Section 3, meet the latch.
Okay, so what exactly is doing the remembering inside that feedback loop? Well, it's time to meet the absolute foundational building block of all data storage, the latch. A latch is a 1-bit memory element. It's designed using those clever feedback loops we just talked about, allowing it to store and hold a binary state, so a 0 or a 1, indefinitely. And here's the real kicker. It does this asynchronously. That just means it holds the data perfectly steady without needing a master system clock to tell it what to do, just as long as the circuit has continuous power.
Basically, a latch is what we call a bistable device. Think of it exactly like a seesaw on a playground. It can rest perfectly stable in one of two states, tip to the left for a 0 or tip to the right for a 1. Once it's in that position, it just remains in that state indefinitely. Well, until an external signal comes along and forces it to change balance.
Let's dig a little deeper in Section 4, the SR Latch explained.
So knowing that a latch acts like a seesaw is great, but how do we actually go about pushing it up or down? Enter the active high SR latch, or set-reset latch. This guy has two main inputs. If we send a signal to the S or set input, the output shoots right up to a 1. If we send a signal to the R or reset input, the output drops down to a 0. And if both S and R are 0, it does absolutely nothing. It just stubbornly holds on to whatever memory state it currently has.
Looking at the table, you can clearly see those hold, reset, and set operations in action. But I really want you to pay close attention to that dreaded invalid or undefined state at the bottom. If you accidentally trigger both the set and reset inputs at the exact same time, like setting a 1 to both, the circuit gets utterly confused. It's literally like trying to push a seesaw up and down simultaneously. In logic design, this is a massive warning sign. We absolutely cannot let this happen.
All right, in just a second, we're going to look at a timing diagram to see this in action. Now, to make sure you're feeling totally confident and not overwhelmed, just remember this simple 3-step rule for reading these waveforms. Step 1, check your input lines at a specific moment in time. Step 2, compare those inputs to the truth table we just learned. And Step 3, determine what the new output state should be. Pretty easy, right?
Let's actually put that into practice. If we trace the Q output line over time, you'll see when the set input pulses, Q jumps high to a 1. But watch what happens when that set pulse goes away and drops back down to 0. The output stays high. It successfully remembers its state. It holds that 1 completely steady until later down the timeline when the reset pulse finally kicks in, dropping the memory back down to a 0. It is actively remembering, which is just so cool to see.
This brings us to Section 5,
taking control with gates.
So our SR latch is incredibly cool, but as an engineer, it's got a pretty critical design flaw. It is way too sensitive. Because there's no clock, it responds immediately anytime an input shifts. Which brings us to a massive rhetorical question. How do we update memory only at specific times? What if we want to isolate it so random stray electrical noise doesn't accidentally wipe out our stored ones and zeros?
To solve this, we introduce something called the enable gate. I absolutely love the visual metaphor of a heavy, locked wooden door to represent this. Think of the enable input, or EN, just like a physical door protecting the latch. When the door is closed, the latch is completely shielded and just ignores all outside inputs.
Now, when we wire this door into our circuit, we get the gated SR latch. We've basically added an enable switch to turn the whole thing on or off. When the enable input is low, a 0, the door is closed, the latch is disabled, and it stubbornly holds its previous state. It's perfectly safe. But when the enable input is high, a 1, the door swings wide open, the latch is enabled, and it behaves exactly like that regular SR latch we already know.
Let's see how this translates into our waveform diagram. Do you see the clever little trick here with the enable pulse? The set and reset inputs can be jumping around all they want, doing whatever. But that bottom Q output only ever changes state during the brief windows when the enable pulse is active. We are now dictating exactly when the memory is allowed to learn new information.
Okay, so we have control over time, but we still have one lingering problem. That pesky, dangerous 1-1 invalid state where both set and reset are triggered. To fix this permanently, engineers came up with a final, brilliant upgrade, the gated D latch. The D here stands for data. We've actually replaced the separate set and reset pins with a single data input, and we placed an inverter, that little triangle symbol you see, right between them. Because of this single inverter, the top gate and the bottom gate will always receive opposite signals. It is now physically impossible for the latch to receive a 1 and a 1 at the exact same time. Our memory is officially foolproof.
The true beauty of the D latch is just its elegant simplicity. Look at the table. If enable is 0, the output doesn't change. Done. If enable is 1, the output perfectly mimics whatever the single data input tells it to be. So if D is 0, memory is 0. If D is 1, memory is 1. We have eliminated that invalid state completely.
And our final waveform confirms this perfectly. When the enable line goes high, the output just copies whatever the D line is doing. And when enable goes low, the output locks in horizontally, holding that memory completely stable. It's beautifully predictable and offers absolute, undeniable control over our data storage.
Let's do a quick wrap-up of our complete memory upgrade journey today. We started with combinational logic, which gives us instant math but zero memory. We then introduced sequential logic, utilizing those brilliant feedback loops. That gave us the basic latch, a 1-bit memory element holding data on a seesaw. We then bolted on an enable gate to act as a security door. And finally, we added an inverter to create the gated D latch, giving us totally safe, predictable, and controllable data storage. So, we have successfully built the atomic unit of digital memory. But here is the massive question I want to leave you with today. Now that we know how to securely lock away a single solitary 1 or 0, how on earth do we chain billions of these microscopic latches together to build the massive gigabytes of memory sitting inside the phone or computer you're using right now? That is the next incredible leap in digital logic design, and I really can't wait for you to discover it. Keep learning, keep exploring, and we'll see you on the next explainer.